Welcome back to G Fun Facts Online. Today, we are heading south, far south. We are going to the bottom of the world, to a place that functions as the lungs of our planet, yet paradoxically, struggles to breathe itself. We are talking about the Southern Ocean. It is a place of extremes. It is a graveyard for explorers and a nursery for the most vibrant life on Earth. But deep within its freezing, churning waters, a ghost story is unfolding. It is not a tale of haunted ships or spectral sailors, but of a chemical specter, a trace element so scarce, yet so powerful, that its presence or absence dictates the fate of continents. This is the story of the Ferrous Phantom. It is the story of the iron that bleeds from the dying Antarctic ice, and the biolock, the microscopic biological mechanism that might just hold the key to our climate's future. To understand this phantom, we have to look at the chemistry of the water itself. For decades, scientists looked at the Southern Ocean and scratched their heads. It was a baffling contradiction. By all chemical logic, these waters should have been teeming with life. They were rich in nitrates, phosphates, and silicates. These are the macronutrients, the fertilizers that fuel the growth of phytoplankton, the microscopic plants that form the base of the marine food web. In almost any other ocean, if you dump these nutrients into the water, you get an explosion of algae. But the Southern Ocean remained desolate. It was classified as a high-nutrient, low-chlorophyll zone, or HNLC. The table was set, the food was piled high, but the guests, the phytoplankton, refused to eat. The waters remained a clear, sterile blue, rather than the murky, life-filled green of a productive ocean. This paradox haunted marine biologists for years. Was it the cold? Was it the lack of light during the long polar winter? Was it the turbulence of the screaming 60s winds? In the late 1980s, an oceanographer named John Martin proposed a radical solution. He suggested that the ocean wasn't missing food, it was missing a vitamin. It was missing iron. Specifically, element number 26. Iron is essential for photosynthesis. It forms the core of the enzymes that allow plants to harvest energy from sunlight and fix nitrogen. Without iron, phytoplankton cannot process the abundant nitrates and phosphates around them. They starve in the midst of plenty. Martin's hypothesis was famously bold. In a lecture that would become legendary, he declared, "Give me a half-tanker of iron, and I will give you an ice age." His logic was terrifyingly simple. If you add iron to the Southern Ocean, the phytoplankton will finally be able to bloom. They will consume the nutrients, grow exponentially, and in doing so suck massive amounts of carbon dioxide out of the atmosphere to build their bodies. When they die, they will sink to the ocean floor, dragging that carbon down with them. This process is known as the biological pump. If you did this on a large enough scale, Martin argued, you could scrub the atmosphere of CO2 and cool the planet, mimicking the natural dust events that triggered ice ages in the distant past. Martin died before he could see his theory fully tested, but his iron hypothesis birthed the concept of the Ferrous Phantom. We realized that iron was the ghost in the climate machine, invisible, trace, but omnipotent. And now, nature is conducting John Martin's experiment for us. This brings us to the bleeding continent. Antarctica is not just a block of ice. It is a continental vault. For millions of years, the ice sheet has been scraping against the bedrock of the continent, pulverizing mountains into dust. This is known as glacial flour. This flour is rich in minerals, including iron. As long as the ice remained frozen, this iron was locked away, entombed in the glaciers. But the vault is cracking. Anthropogenic climate change has destabilized the Antarctic ice sheets. The Thwaites Glacier, often called the Doomsday Glacier, is retreating. The Pine Island Glacier is thinning. As these behemoths melt, they are not just releasing fresh water, they are releasing the Ferrous Phantom. There are three main ways this phantom escapes its icy prison. First, there is subglacial runoff. Beneath the ice sheets, rivers of meltwater lubricate the glaciers slide into the sea. These rivers scour the bedrock, picking up dissolved iron and iron-rich particulates. When this discharge bursts out from under the ice shelf, it shoots a plume of nutrient-rich water into the ocean. Second, we have iceberg rafting. As ice shelves fracture, they birth massive icebergs that drift north into the Southern Ocean. These icebergs are dirty. They carry trapped sediment and dust. As they melt in warmer waters, they leave a trail of iron filings behind them. This is fertilization by rafting. Satellite imagery often shows bright green streaks of phytoplankton trailing behind melting icebergs, like a ghost's footprint. Third, there is atmospheric dust. The retreating ice exposes bare land. The fierce katabatic winds that roll off the Antarctic plateau whip this newly exposed soil into the air, carrying iron-rich dust hundreds of miles out to sea, where it settles on the waves like manna from heaven. This creates a fascinating and ironic feedback loop. The heat melts the glacier. The glacier releases iron. The iron feeds the The plankton suck up CO2. The atmosphere cools. It sounds like a perfect planetary safety valve, a biolock. But biology is never that simple. Let's delve into the mechanics of this biolock. For the Ferrous Phantom to save us, it is not enough to just make the ocean green. The carbon has to sink. The process begins with the bloom, or the awakening. When the iron hits the water, the response is almost instantaneous. Diatoms, the jewels of the sea, are the first to respond. These microscopic algae are encased in ornate silica shells. They begin to divide rapidly. Within days, a patch of blue ocean turns into a thick, murky soup of biological activity. During this phase, the diatoms are aggressively harvesting CO2 from the surface water. The bloom acts as a giant sponge, scrubbing the sky. But a bloom does not go unnoticed. This leads to the second phase, the graze, or the war. The grazers arrive. Copepods, krill, and salps swarm the bloom. Antarctic krill, likely the most successful animal species on the planet by biomass, feast on the diatoms. This is a critical juncture for the biolock. If the krill eat the algae and respire the carbon back out as CO2, the lock fails. The carbon returns to the cycle. However, krill are messy eaters, and they produce massive, heavy fecal pellets. This leads to the third phase, the export or the descent. For the biolock to engage, the carbon must cross the sequestration depth, usually defined as 1,000 meters down. This is the twilight zone. The primary vehicles for this descent are marine snow and the diatom die-off. Marine snow consists of dead diatoms, krill poop, and other organic debris clumping together. As they fall, they are colonized by bacteria, making them sticky, gathering more dust and debris. This snow drifts down, carrying the carbon locked in its chemical bonds. Alternatively, sometimes a bloom grows so fast it exhausts all the silica in the water. The diatoms, suddenly unable to build their shells, die en masse. Their heavy glass shells act as ballast, dragging their organic bodies rapidly to the abyss. Finally, we reach the burial, or the lock. If the material reaches the abyssal plain, miles deep, it can be buried in the sediment. Once there, that carbon is removed from the atmospheric cycle for geological timescales, potentially millions of years. This is the final click of the biolock. The Ferrous Phantom has delivered the key. The diatoms have turned the key. But here's the catch. The door doesn't always lock. Recent studies, including work published as recently as 2026, have cast a shadow over the optimistic iron hypothesis. It turns out, the Ferrous Phantom is fickle. There is a phenomenon known as the rusty disconnect. A major study analyzing sediment cores from the Pacific sector of the Southern Ocean revealed periods in Earth's history where iron levels were incredibly high, yet algae growth did not increase. The biolock did not engage. Why? One reason is the ligand limit. Iron in seawater is tricky. It doesn't like to stay dissolved. It wants to rust and sink as useless particles. To stay bioavailable for plankton, iron needs to bind to organic molecules called ligands. If there aren't enough ligands, which are often produced by bacteria, the extra iron from the glaciers just precipitates out of the water before the plankton can use it. It is like raining food on a population that has no hands to catch it. Another issue is the dark limit. As the ice melts, it releases iron, but it also releases fresh water. This fresh water is lighter than salt water, so it sits on top, creating a stratified layer. While this keeps the plankton near the sun, it can also trap them in a layer that quickly runs out of other nutrients, like silicate. If the diatoms run out of glass for their shells, the iron doesn't matter. They crash before they can sequester significant carbon. Furthermore, we have the zooplankton short circuit. In some recent observation events, the krill and salps were too efficient. They ate the blooms so fast that the carbon remained in the upper ocean, recycled through respiration. Instead of a carbon sink, the bloom became a carbon roundabout. And then there is the bacterial hijack. When a bloom dies, bacteria attack the sinking carcasses. This decomposition process consumes oxygen and releases CO2. If the bacteria are too active in the upper water column, they convert the organic carbon back into gas before it can sink. This is known as remineralization. Warmer oceans boost bacterial metabolism. So as the ocean warms, the bacteria work faster, unlocking the biolock before it can be secured. The Phantom brings the iron, but the heat brings the thief. Despite these uncertainties, the allure of the Ferrous Phantom is irresistible to policymakers and corporations, desperate for a climate magic bullet. If nature is doing it slowly, why don't we do it faster? This is the controversial world of Ocean Iron Fertilization, or OIF. Several unauthorized and semi-authorized experiments have already taken place. The most infamous was the 2012 Haida Gwaii project, where a businessman dumped 100 tons of iron sulfate off the coast of Canada, triggering a bloom visible from space. He claimed it restored the salmon fishery and sequestered carbon. The scientific community called it rogue geoengineering. But the conversation is shifting. With the climate crisis accelerating, legitimate research institutions are revisiting OIF. They are looking at precision fertilization, using autonomous drones to release small, controlled amounts of iron in eddies, where it is most likely to trigger a locking bloom. But the risks are massive. What if the iron triggers the wrong kind of algae? Pseudonychia is a diatom that produces the neurotoxin domoic acid, and it thrives on iron. A massive, artificial bloom could poison the entire food chain. Or consider nutrient robbing. If we force a massive bloom in the Southern Ocean, it consumes all the macronutrients. These nutrients would normally drift north to feed the fisheries of the equator. By locking them up in the Antarctic, we might starve the tropics. And perhaps most frightening is the risk of anoxic zones. If the bloom is too big, the decaying matter sinking down could suck all the oxygen out of the deep ocean, creating dead zones where nothing can survive. We are attempting to harness a phantom we barely understand. The most gripping part of this story is the race currently happening on the Antarctic coast. As you listen to this, the Thwaites Glacier is pumping meltwater into the Amundsen Sea. This water is rich in dissolved iron. Satellites are picking up anomalous chlorophyll events, massive blooms in open water areas surrounded by sea ice. Scientists are observing a phenomenon called the Green Ring, a band of intense biological activity encircling the continent, expanding as the ice retreats. This green ring is the biolock trying to close. But new research suggests this ring is a double-edged sword. Green water absorbs more heat than blue water. By darkening the ocean with life, the Ferrous Phantom might inadvertently be warming the water around the ice, accelerating the melt. One blade of the sword sucks CO2 and cools the atmosphere. The other blade darkens the water and melts the ice. Current models are conflicted on which blade cuts deeper. Looking forward, we are entering the Ferrous era of the Southern Ocean. As the ice sheet collapse becomes irreversible in certain sectors, the influx of iron will increase by orders of magnitude. We are moving from a scarcity economy to a surplus economy. This will fundamentally restructure the food web. Some models predict the rise of the gelatinous. The new chemistry might favor salps and jellyfish over krill. Salps are efficient carbon sequesters because their pellets sink fast, but they are poor food for whales and penguins. We might get a biolock, but at the cost of the charismatic megafauna. The Southern Ocean could become a silent, jelly-filled carbon factory. Speaking of whales, we cannot ignore the whale pump. Baleen whales play a crucial role here. Blue whales and humpbacks consume massive amounts of krill, which are rich in iron. When whales defecate, they release plumes of iron-rich manure at the surface, recycling the iron and keeping the phantom active. Commercial whaling in the 20th century decimated this pump. By killing 99% of the blue whales, we broke the recycling loop, making the Southern Ocean more iron-poor. The recovery of whale populations is, strangely, a geoengineering project in itself. More whales means more iron recycling, which means more blooms and more carbon sequestration. But there is also the terrified possibility of the deep carbon burp. As deep ocean circulation changes, specifically the slowing of the Antarctic bottom water, the ancient carbon stored in the abyss might be burped back up. The Ferrous Phantom is trying to push carbon down, but the changing currents are trying to push it up. We are no longer passive observers. The Ferrous Phantom is now a variable in our climate models. Startups are modeling iron credits, proposing that if they can prove a glacier melt event sequestered carbon, a nation should get a credit. It is a perverse incentive. Let the ice melt, because the melt saves the planet. This logic is dangerous. It ignores the loss of habitat, the sea level rise, and the chaotic unpredictability of the biolock. In conclusion, the Ferrous Phantom is not a savior. It is a symptom. The massive blooms of green swirling off the coast of Antarctica are the bruises of a battered planet. They are the immune system of the Earth kicking into overdrive, trying to clot the wound of rising CO2 with biological mass. The biolock is real, but it is fragile. It is a rusty biological mechanism trying to hold back the tide of the Anthropocene. To pin our hopes on it is folly. Yet, there is a sublime beauty in the mechanism. The fact that the death of an ice sheet can birth a trillion lives in the ocean. That a single atom of iron, eroded from a mountain peak millions of years ago, can be the catalyst for a microscopic diatom to capture a molecule of carbon exhausted from a tailpipe in London or Beijing. It connects us all, the rust in the rock, the ice in the south, the gas in the air, and the blood in our veins. The Ferrous Phantom will continue to haunt the Southern Ocean. Whether it acts as a friendly ghost, locking away our excess carbon, or a poltergeist, disrupting the food web and darkening the seas, depends on the delicate, chaotic dance of biology and physics. But one thing is certain. The Antarctic is not silent. It is speaking to us in the language of blooms and currents, of iron and ice. And we need to listen, before the lock breaks for good.